Hello, everyone. This is the next run. This is Calculus from the University of South Florida. I'm Scott Grizzard. And today we are talking about antiderivatives, and we're talking about estimating the Auc function. So last time we talked about the fundamental theorem of calculus, and then today we had a quiz. We'll go over the quiz. Are there any questions? Okay, so has everyone found this assignment that is on the for the curve for test 3? So of course your tests were returned to you. Please keep requesting regrades. That actually, because I didn't go through every problem, I went through the major ones that normally have, are difficult to grade, but I didn't go through every single one of them. So if you notice inconsistencies, please, by all means, hit the request regrade. I love this feature. It gives me a direct link. I'll be happy to talk about it during office hours if you want to with you. I'll be happy to go over your test. I love this thing. It's now I'm now like going around lobbying for Gradescope. I'm like, can we have for regular semesters? I love this thing. So yeah, and the average keeps going up. So you guys are requesting regrades. I'm looking at it. I'm like, yeah, you deserved a point here. Ooh, this is totally graded wrong. That should deserve points. And the average keeps going up, which is making me very happy. So by all means, request regrades if you decide that something's needed. Look at your test. I also uploaded test 1. If I find where I put the files for test 2, they may be on my computer in my office. But I'm pretty sure I put them on a thumb drive somewhere when this whole thing happened. I'm pretty sure I stuck them on my thumb drive, and I just need to find them. So the files, if I find the files for test 2, I will upload test 2 also to the Gradescope, so you can get that, because I know people lose those things and need them to study for the final. So did everyone find this curve assignment? So, I mean, I don't know if you care, but there was this whole, fussing about, some professors just wanted to give us, some instructors just wanted to give a curve. Others, there was, no, we can't do a curve type thing. And we wound up with this compromise that we're going to let you do test corrections. As you can tell, it looks just like, well, almost just like the assignment I gave you, the problem set I gave you after the test. Last time it was going to be the problem set for this time, but they stole my problem set and gave it test points instead of just quiz points, and made it a curve. So it's as a further inducement, even if test 3, okay, even if test 3 is the one you drop, you get to keep the 10 points. That's not happening for all the classes, but I'm doing that. So that's, even if you're going to end up dropping test 3, you get to keep the points, right? They'll go on test 1 instead of test 3. All right. Are there any questions about that? Basically, I'm entering it in as a quiz out of 0. I'm sorry, as a test out of 0 points, and I'm giving you, between 1 or 10 based on what you do here. So let me just go over this very briefly. I did it in the previous class, and please type your questions. So yes, you're going to upload your corrections. No, you do not need to do your corrections over Proctorio. This is an assignment, okay? So what you're going to do is you're going to do your test corrections, and you're just going to upload them to Gradescope. I did say Gradescope, right? I didn't say Proctorio, because I sometimes do that. All these systems, yes, no. You're just going to upload it to Gradescope, okay? Now, a couple things about this thing. Last time you could get away with doing just parts of questions. This time, if you are doing one of the questions with multiple parts, you have to do the whole thing again. Okay, so you have to actually give a fair solution for all of your things. Secondly, I'm no longer giving you free pass, because these are actual now test points. I'm no longer giving you a free pass on the if you didn't miss any or just missed a few. Okay, so if you run out of questions from test 3 that you missed, there are 5. This thing has 5 parts to it. If you run out of test 3 questions, go back test 1 and answer questions from that. So what you're going to do to make sure that everyone understands what's going on, so what you do is you circle the problem that you're doing. If it's a test 3 problem, you circle this one. If it's one of the test 1 problems, you can see that 3 C, D, and E are grouped together, and 3 F, G, and H are grouped together. So if you choose one of these two, you have to do all 3 problems, all 3 parts of that problem on that page. So if you run out of problems from test 3, go to test 1. If you run out of problems that are on the list, go to problems that aren't on the list. If you run out of, if you run out of problems even then, go to test 2. And if you're still out of problems, go dig up a quiz that you didn't do well at. Okay, I want you to actually do these things because it's not just to torture you. It's also because I want you to review the cumulative portion for the exam. All right. So are there any other questions about this? So 1 to 5, how do we feel about this assignment? How do we feel about understanding what exactly is expected of you? You know, it's just like this. They basically stole my old one. This was going to be the problem set, but now we're giving you real points. So and I actually worked it out, and it works out that it's 1.45 something points on your final grade, this 10 points. That's what 10 test points work out to, if you're wondering. So that's the assignment. You're just going to upload it to Gradescope. There's no Proctorio for it. Are there any other questions? And it's open book, open note. You can collaborate, but you have to all write your own fair solutions. And I really want you to work on that. If you miss, no, this is not the Nagle replacement. I'll get to that in a moment. Okay, so if for some reason you miss if for some reason you still don't understand a problem, I will be happy to walk you through it. We'll talk about it, come to office hours, because I want you to turn in really good fair corrections. Are there any other questions about that? Okay, so this right here is the beautiful compromise. You get to keep the points even if test 3 gets dropped. And the purpose of the assignment is really to help you prepare for the final, not just, do test corrections and, heaven forbid, learn the material. But also, now, if one of the questions you missed was the optimization problem, and if you really missed it, not, oops, I dropped the 0, which happened a lot, right? Some people dropped one of the zeros off 45,000. But if you actually missed the problem, you didn't understand it, please do that one. As one of your problems, because that's an important thing. Are there any other questions? Comments, issues, suggestions, thoughts about this? All right, Nagle replacement. The Nagle replacement, I've decided what I'm going to do is next week or the week after, instructor evaluations are going to come out where you fill out your student instructor evaluation. What I'm going to do is everyone that fills it out, I don't know, I'm not going to ask you what you said, but everyone that fills it out gets a point on their final grade. So that's going to be the Nagle replacement thing. I'm going to give, there's going to be an assignment. What you're going to do is upload the screenshot that says that you did it. And when you do that, everyone gets when you do that, the TA is going to look through it and go, yep, you did it. 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 You need to do a screenshot of where your name is and the fact that mine is complete. And there'll be like an example of how to do it and everything. That'll be the extra point. So 1 to 5, how do we feel about these two things? All right. So we seem to be on board with these assignments. Okay. Any other questions before we begin? Any other questions? Okay. So basically, that's what's going on. We had a plan that, I was going to have extra credit that stays. And then we have this new thing because some sections did horribly on the exam. Some sections did very well. You just made my day with your scores. And then don't forget that tonight is the 5 p.m. problem set. If you didn't do well on the test, please come. We'll talk about stuff. And I've also got office hours where I'll be happy to go over tests with you. Are there any other questions? Okay. So let's go over, so today what we're going to talk about after the quiz, let's do the quiz first. Okay. So this will be on every single quiz until the end of class. State the fundamental theorem of calculus. The points will start being decreased, and it will be on the test. I'm giving you a test question. This will be on the test. I'm giving it away. Giving it away that there's a test question that says state the fundamental theorem of calculus. Everyone on board with that? Okay, so there are a couple things you could do. This right here, this condition can actually be stuck on the bottom. So this refers to this, so I could write the word where, and I could just write this under FTC2, or I can make it a condition like I did in class last time for the 11 o'clock, and it goes right there. Either way's fine. What was the other statement? Yeah, so either way's fine. So are there any questions about this one? 1 to 5, how do we feel about this? Right, the statement of this thing and what this thing is saying. And again, on every test, every quiz, going to be on the test, guaranteed. My TA will tell you it was on the test, right? When I told you, when you were taking my class, and I told you it was going to be on the test, was it on the test? Am I lying to you that it's going to be on the test? Am I lying to you that it's going to be on the quiz, on every quiz? You can use the one in the book. I advise you to use this statement. This statement is actually stronger than the one in the book. Also, you don't have to remember, was the interval open? Was it closed? Yada, 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 yada. So this was on the test. This is on the test. I'm guaranteeing it, etc. You can use the one in the book, but you have to get the book one perfect. And it's the book one's more confusing, in my opinion. Now, if you've already memorized it because you took Calculus BC in high school, or for whatever reason, you can certainly use the one in the book. But I recommend this version. It's easier to remember, and it's a bit more powerful. Okay. Now, let's talk about this one. Sorry, I need to get to the thing on this one. Quiz, rubrics, this one. All right. So I asked you to do something that I didn't tell you how to do in class. I asked you, so I assigned a web assign that was, by the way, there's no web assign tonight. I want you to work on the test things. Please don't wait till Saturday or Sunday to do it. I intentionally did not assign a web assign tonight in order for you to work on the test corrections. Okay. So I want you to, I initially had it due on Friday, but there will be a web assign due tomorrow. And I know that people wait till the last minute. So I was like, okay, well, there's a web assign due tomorrow. So I'll make it, I didn't post it yet, did I? All right, I'll post it sometime today. There will be a web assign due tomorrow, but there's not one due tonight. I want you to work on test corrections. I want you to ask me questions. Come to the 5 p.m. thing. That's why I'm not assigning a web assign tonight. It's not that I don't love you and I don't want you to work on problems. It's that I want you to focus on nailing the rest of the stuff that you missed from test 3 and test 1, if that's it, etc. So last night, anyway, there was a web assign with a video, and I asked you to do that. There were 2 videos. And the idea here is that we want to get at how you compute, how you find antiderivatives, what an antiderivative is, and then how do you find them. So what I'm going to do is there's a couple tricks. The first trick is deal with exponents first. So what I'm going to do when I deal with the exponents first is I'm going to do this. Okay, I've got f of x equals x cubed plus 2. Now, I've got this thing. This thing is really x to the 0, right? There's a 1 there, and that's really x to the 0. And the last thing is that this is actually plus 0. Okay? So now when I do my antiderivative, okay, I'm going to work backwards. I'm going to use the capital letter F, and I'll get to the difference between these things later. The first thing I'm going to do is I'm going to put the x to the 4th here, right? Because when this thing happened, when I took x to the 4th, if I had x to the 4th, I'm going to wind up with a 3 there when I take the derivative. How do we feel about that, 1 to 5? Okay. All right. So what I'm going to do, now when that 4 comes down, it's going to come in front as a 4th, right? I'm going to wind up with 4x cubed. So what I'm going to do is I'm going to need to get rid of the 4. And in order to get rid of the 4, I'm going to multiply the front by 1/4. Because now when that 4 comes down, I'm going to wind up with 4 over 4, which is 1. Then I'm going to have an x to the 1st here. But that x to the 1st, that 1 is not going to do anything when it's multiplied in front. So then I'm going to add a 2 here. And that will give me that 2x to the 0. Now, I'm going to need a constant here, because that constant is going to go to 0. And I'll get into why we call it c in just a moment. How do you feel about that, 1 to 5? Okay. Yes, you could use the method from Webassign, but the method from Webassign asks you to memorize. Okay? And this is the thing. I'm not asking you to memorize a formula. I'm asking you to think about what's going on backwards. Okay? Now, the method from Webassign is perfectly fine, but I'm asking you to think about what happened. I'm asking you to actually dig into the thing. Okay? Now, I'm going to explain exactly how I got from 3 to 4. The way I got from 3 to 4 was this, and I cannot stress this enough. Always check your antiderivative. Always take the derivative of your antiderivative. Here, I actually required you to do it. Right? I said check. So what I'm going to do is I'm going to do f prime of x equals. Now, I'm going to do 1/4 times 4 x to the 4 minus 1 plus 2x to the 1 minus 1 plus 0. And then that is the exact same thing as that. Those two things are equal. Yes, you will lose points for not snailing the C, because I asked for the general antiderivative. Okay, not an antiderivative, the antiderivative. Now, why did I add the 0? I added the 0 to remind myself to deal with the constant, right? So when I took the derivative, that c went to 0. Now, to go back to the question, how did I go from 3 to 4? I went from 3 to 4 because when I took the derivative, I'm going to subtract 1. And that's why I'm saying deal with the exponents first. When you've got a polynomial or anything that is in an exponential form, deal with the exponents first, okay? Add 1 to the exponent and then figure out what has to happen to the term in front, okay? How do you feel about that, 1 to 5, that process? Yeah, so C is just for the general one. Okay. All right, now let's do this one here. AUC F0 of X. Well, I'm going to do AUC F0 of X equals, by the fundamental theorem of calculus, part 2, okay, G of X minus G of 0 where G prime of X equals that, okay? So I want a function whose derivative is x cubed plus 2. Well, I just took one, okay? What I'm going to do is I'm going to use this thing here, but with a constant of 0. I get to pick any function whose derivative is this thing. So I'm going to use f, but I'm going to let my constant be 0. I don't care what the constant is, okay? It will add and subtract out. So I'm just going to use 0 as my constant and make my life happy. So that is going to be 1/4 x to the 4th plus 2x minus 1/4 0 to the 4th plus 2 times 0. And both of those terms go away. And I wind up with 1/4 x to the 4th plus 2x. So, all right, so now there's a question, how do we feel about that, 1 to 5? And while you're posting that answer, I'm going to answer the question that's in chat. Do I mean something different when I ask for the general antiderivative as opposed to just the derivative? No, actually, I mean something different when I ask for the general antiderivative versus an antiderivative. Okay? Now, the other question is, can you use FTC1? You actually can, but it's rather, difficult. Because you need to deal with the fact that there's a base point there. So it really is FTC2. Okay. I mean, I could, but then I'd have to mess around and figure out what the A was, and then I'd have to use a general antiderivative, and then I'd have to mess around with the A, and I'd actually have to solve for the constant. The constant would be 0 in this case, but I'd actually have to solve for that. It's easier to use FTC2 here than FTC1. Are there any other questions? Okay. All right. So now the question is, do I have to write that? Yes. You have to write two things. I want the general antiderivative, so I have to write the C. I need to write the FTC too. I have to state this theorem if I'm using it in this context. And I have to write the zero term here. Those things have to be written. Are there any other questions? Okay, let's move on to number 3. Okay, so for this thing, I'm actually asking the exact same question that I did before. And you'll see that this is going to happen a couple times. Okay, now, the exam is cumulative. And I'd like to say it's, 50%, no, 40% old material and 80% new material. Now, what do I mean by that? This is a perfectly good example of that, right? Because what is this question exactly the same as? Question I asked on test 3. Right? Of course, it's continuous this time. But now, I've got a twist. I've got a nice little area under the curve, module 4 twist on this problem. And that is that I'm asking for A. So I'm asking for the area under the curve of this function. That's a little, so it's a test 3 problem with a test 4 twist. And I like those things. So to do this problem, I'm going to remember the following little chart. Right? I have F, I have F prime, I have F double prime. And remember, if F is increasing, that means that F prime is positive. And if F double prime is positive, F prime is increasing, F is concave up. Okay? Well, now I've got this thing called A on top, the AUC function. And F is its derivative. So that means that when F is increasing, A is concave up. And when F is positive, A is increasing. How do we feel about that 1 to 5? Okay. All right. So I'm going to use the exact same technique I did for test 3. I'm going to say things about F, and then I'm going to say things about, and then I'm going to see what that means for A. Okay? So here, F is positive. And it's decreasing. Here, F is positive and decreasing. Here, F is negative but decreasing. Here, F is negative, decreasing. Here, F is negative, increasing. And here, F is positive, increasing. That means that A is increasing, concave down, increasing, concave down, decreasing, concave down, decreasing, concave down, decreasing, concave up, and increasing, concave up. How do we feel about that 1 to 5? Okay. So it's the exact same process I would have done for test 3. Okay. So now what do I do? Now I just do what it is. So somewhere I had to write that A prime equals F, but that's a justification for the whole thing. Okay. So somewhere I had to write that. Okay. And then I just do the problem like it was before. A is decreasing over 0, 3, because that's where A prime is negative. Critical numbers of A are 0 and 3, for that's where A prime equals 0. There's no place where the derivative doesn't exist. F is concave down over negative 2, 2, because that's where F is decreasing, and F is the derivative of A. A has a local maximum at x equals 0, because that's where F goes from positive to negative. Okay. I just use that thing. All right. I will come back to this. If you're having troubles with this kind of concept, we will talk about it. Now, are there any questions about this problem? How come 2 isn't a critical number? Because 2 is a minimum for F. So it would be a critical number for F, but it's not a critical number for A. Okay? It is a critical number for A prime, but not for A. Here it's an inflection point. This is an inflection point, by the way, for A. Are there any other questions? Okay. All right. So now what I'm going to do, you can, if you've missed part of this while you're trying to take notes, you can, of course, view the video and go back. I'm going to skip ahead to the class. Just out of curiosity, is anyone bothered by the fact that this is -1 and I'm asking over the interval -2 to 4? What does it mean to be left of the endpoint? Right. So if I'm looking at this problem here, and I'm asking about area, right? I'd sit here and I'd go, okay, from the base point here, this is positive area as I move to the right. So I'm increasing. This here is negative area as I go to the right. This is negative area as I move to the right. This is negative area as I move to the right. And this is positive area. But what about this section right here? What's going on with that? Well, it's easy to talk about negative area because that is at least has a concept that can be related to physics in terms of distance, right? I could have displacement, which is like velocity with, it's distance with direction, okay? So if I'm just like on the unit circle, as you recall, on the unit circle, I could be negative east of the center of the mascot's nose, right? If I'm at the unit circle, if I'm talking about eastiness, when I'm here, I'm positive if I have a circle. But then as I go over, I don't know if you guys can see that little cursor, but as I go over, I have negative eastiness on this side. Okay. Well, the same thing works for the area, right? So I have this idea where I'm negative area. But what about when I'm left of the base point? Well, I want to define being left of the base point in a way that makes the FTC, the fundamental theorem of calculus, work. Right? So what I'm going to do is I'm going to construct a definition of being left of the endpoint that makes that work. Okay? So if I'm here, right, here my base point is 2. And my function here is f of x equals x. I'm shooting at the wrong place. So when I'm here, I've got no area because I've got no width. And then as I move to the right, I add positive area. 1 to 5, how do we feel about that? I'm sweeping out positive area under this function. And again, the function should already be drawn, but it's not because I'm using an old version of the program. So the function's already there, but I left the new version of the program on my computer at the office, and I didn't go back. If your test twos, if I have to go back for your test twos, I'll probably grab the program while I'm there. Not that it'll do as much good because now I'm done. But if I'm left of the base point, I'm going to define being above the x-axis as negative area. Okay? So here I'm saying I'm measuring the area from 2 to x equals 0. From 2 to x equals 0. And because I'm left of the base point, I'm going to call it, and above the x-axis, I'm going to call it negative area. So when I'm at 0, my area under the curve is negative 2. Because the area of this figure is 2, but it's left of the base point. Okay? How do we feel about that, 1 to 5? Okay. Now, the reason I define it this way as negative area is because watch what happens when I hit play here. When I hit play, I start taking away negative area. So as I move to the right, I'm taking away negative area as I approach my base point. Right? I've got less negative area. And that means my derivative, my area under the curve is getting less negative. Right? And less negative means more positive. I'm getting less and less negative, right? Because I'm getting rid of negative area, which means my area under the curve is increasing. Does everyone see that? Here, I had more negative area than I do here. Here I've got less negative area. And that means that the area under the curve function is going from bigger negative to closer to 0 negative. Right? It's moving up. All right, my function, my area under the curve is moving up as I approach my base point. So by defining negative area left, defining area left of the base point as negative, okay, I get it to be consistent with the fundamental theorem of calculus. And then I hit play, and it keeps going and going. Right there it was 0. And now I'm adding positive area again as I go to the right. Okay? So when I'm left of the base point, when I'm left of the base point, I'm going to define area like this. I'm negative area if I'm above the axis, positive area if I'm below. This way, as I move to the right, if f of x is above the x-axis, I'm taking away negative area, making it consistent with FTC1. So if we look at another example of that, here, I'm going to start below the axis. So on the left, I'm below the x-axis. So everything, and my base point here is 0, and I'm starting from -2. So this is now negative area because I'm left of the base point, and this is positive area because I'm below the axis but left of the base point. 1 to 5, how do we feel about that? So if I've got, oops, that's quiz rubrics. If I'm left of the base point and above the axis, right, I get negative signed area. So if I'm right above positive, right below negative, left above negative, left below positive. Okay. So if I look at the animation, if I start way over here and then I hit play here, what's going to happen? Well, now I'm losing negative area. Let's slow this down. So as I move to the right, right now I'm decreasing my amount of negative area. I'm sorry, positive area. So my f is below the curve, my f of x is below the curve, and my derivative is negative because I'm reducing the amount of, as I move to the right, I'm reducing the amount of positive area. Now I'm reducing the amount of negative area. So my derivative is positive. Then I'm going, when I reach the base point, I wind up with a derivative, with an AUC of 0. Now, as I move to the right again, as I keep moving to the right, my AUC is increasing because I'm above the x-axis. And then when I cross the x-axis again, my AUC becomes negative. Right, I'm sorry, my AUC becomes decreasing, not negative. My AUC is decreasing because my function is negative. 1 to 5, how do we feel about that? So that's going to give us 2 new properties of the AUC function. Okay. So that gives us 2 new properties of AUC. If I have no width, I have 0. So if x equals a, I've got no width. And I wind up with 0 as my AUC. Now, if AUC, A, and B are different points in D, and I flip which one's the base point and which one is X, I negate the amount of area, because negative area becomes positive area, right? Stuff that was left of the base point is now right of the base point, and stuff that was right of the base point is now left of the base point. So now I flip the sign. If I flip my endpoints, I flip the sign. Okay? So those are two new properties of the AUC function. All right. 1 to 5, how do we feel about that? These two new properties. If you want to see that one in action, here it is. So here is the AUC plot, where what I've got is I chose 0 as the base point, and 4.5 is X. Is everyone on board with that? So right now, everything is right of the, here's my base point. This is all right of the base point, positive. This is right but below, so it's negative. And this is right and above, positive. Now, if I flip 0 and 4.5, if 4.5 becomes the base point and 0 becomes the X value, watch what happens. I flipped, right? Positive area became negative area became positive area. Because now my base point is way over here. And my X is this 0. Okay? That's that rule in motion. Okay. Any questions about that? Okay. I bet I could put, I wonder if I could put static. No, I'm not going to bother. It's too much. I might break something if I do it. It's not that I don't want to bother. It's just that I might break something. Let's try it. Let's do it anyway. So here I am for negative. That's discrete math. This one. Let's see if I can make that graphic happen here. It did work. Look at that. There it is. I got a nice little graphic of the whole thing happening. Very nice. There they are. And now they're in the notes. So that's me flipping base points. Any questions about that? 1 to 5, how do we feel about that now? Okay. All right. Let's move on. Yeah, I'm not going to make it to the. All right. So let's make sure that I finish the antiderivative stuff, and then I'll get to the rest of it next time. So what I want to do is I want to do some antiderivative stuff, okay? So we've got a couple definitions, and because I'm running out of time, I'm going to cheat a little bit and actually do a little copying and pasting. So if D is an interval and F is contiguous, I want to define what I mean by an antiderivative. So an antiderivative is just any function whose derivative is f. And the fact that D is an interval is actually very important here. Okay. So let's do an example. F of x equals cosine of x plus 2. So an example of an antiderivative would be g of x equals sine of x plus 2x plus 6. Okay. So a function is an antiderivative as long as, you know, the derivative of g equals f. How do we feel about that? 1 to 5. Okay. Now, normally when I talk about an item versus the item, when I talk about the item, I'm talking about a specific item. Yeah, that's not how it works in math. Now, when I talk about the general antiderivative, I actually mean the set of all antiderivatives for f. That's confusing as can all be out. So when I talk about the antiderivative, what I actually mean is the set of all functions whose derivative is f. Okay? All right. So what I mean when I say the general antiderivative is a set, right? I mean all functions g, so that g prime of x equals f of x. Well, remember that I have this theorem, right, from test 3. Okay? And it was the last thing we talked about. I have this theorem that says that if f and g are both defined on an interval d, where f prime of x equals g prime of x, in other words, the derivatives are equal, then I've got their vertical shifts of each other. F and g have to be vertical shifts of each other if f prime of x equals g prime of x. 1 to 5, how do we feel about this statement right here? If two functions have the same derivative, then they have the exact same shape, and the only thing that's changed is the vertical intercepts. Let's see, did I do a nice little graphic for that on one of them? I did. There's the graphic. Well, because of that, I can write this set. When I write this set, I'm just going to write it as g of x plus c. right? Because these two sets are absolutely equal. So this set here equals the same set G plus C, so that G prime of X equals F of X, and for all X and D, and C is some real constant. So I have this generic constant floating around, C. So when I take the antiderivative, okay, I'm going to just take a generic antiderivative. I'm going to add the C. And that's all I'm going to write. I'm not going to write the whole set notation. I'm just going to write that. If this says this antiderivative here, F, is the entire class of functions that C is a real constant. Because all of those functions will give me a derivative of F. How do we feel about that, 1 to 5? That's the difference between the antiderivative and an antiderivative. Okay. Okay. I have 4 votes. The number of votes in chat keeps going down. So are people just not watching? Is that what's going on now? You know, people are like, I'll post the video later. Okay. They're going to watch the old video. They're like, nah, Scott does 9:30 videos better. We're just gonna watch the 9:30. I got it. You're hurting my feelings. No one's asking questions. Okay. Are there any questions? Okay. Yeah. Everyone's using the internet now. Okay. So let's do some tricks for dealing with antiderivatives. One, it is easier to take derivatives. So make a table. And I cannot stress how much easier it is to take a derivative than take an antiderivative. Okay? So make a table. Don't try to memorize that table, that chart of antiderivatives in the book. There's this huge, giant book. Don't bother. Make your own. Okay? So here's what I'm going to do. I'm going to say that I'm going to write on the side here, I'm going to write G first, and then I'm going to write F. And I'm going to say that F equals G prime. And then what I'm going to do is I'm going to work from G to F. Okay? So here's what I'm going to do. The first one I'm going to write down sine. What is the derivative of sine? Cosine. Let's see. Cosine is negative sine. And that means that if I want cosine here, I'm going to write down negative sine here. I'm sorry, negative cosine. Then I'm going to do e to the x, that's e to the x. ln of x is 1 over x. I'm just going to take the derivative. What other derivatives do I have? Tangent is 1 over cosine squared. X to the c is c times x to the c minus 1. Arcsine is what? 1 over the square root of 1 minus x squared. Arc cosine, negative 1 over square root of 1 minus x squared. And that's what I'm going to do. I'm not going to memorize all my bloody antiderivatives, okay? What I'm going to do, the first thing, I'm going to get my test, right? Nice little name page. On the right side of that page where I write my name, I'm going to write this. In fact, on a regular test, I would write this before I wrote my name, okay? But what I'm going to do, of course, here you're going to be able to write your name in advance, and then you have to hold up the fact that it's blank to Proctorio. But the first thing after doing that, before even opening the test, I've shown Proctorio it's blank. Now I'm going to make my little chart. Because it's much easier to go from this direction. Where's my mouse? It's much easier to go from this direction to this direction. It's much easier to start over here, and go this way. It's much easier. Okay? 1 to 5, how do we feel about that? So how do we feel about this idea? I make myself a chart, I make my life happy. So if I wind up with the problem, take the antiderivative of sine, I look at my chart and I go, that's negative cosine. Okay. Step 2, when you're dealing with power rules, do the exponents first. Okay. So let me give you an example. Suppose what I want to do is I want to take the derivative, let f of x equal, let's see, sine of x plus 6x to the 8th. Okay. Is everyone on board with this problem? Now, compute the general antiderivative. So I'm going to have big F here of x. Now, I have a chart. I've made a chart for myself. And the reason I made a chart for myself is now I don't get confused which one had the negative. When I took the derivative of cosine, I wound up with negative sine. That meant when I took the derivative of negative cosine, I wound up with sine. So now I look at my chart. This is what my f is. This is what my big F becomes. Okay? So I go this way now because it's much easier to make the chart and then look at it. So now I've got sine here. I'm going to put negative cosine right there. I'm just going to read it off my chart. Now, here I've got a power rule. All right? So the way I'm going to deal with my power rule is I'm going to deal with the exponent first. I'm going to add 1 to the exponent. I'm going to leave myself some space, and I'm going to do x to the 9th. Now, I'm going to think about the derivative. if I had x to the 9th here, I would wind up with a 9 when I took the derivative. I've got to do something about the 9. If I had just x to the 9th here, when I was taking the derivative, I would wind up with a 9 in front. I need to deal with the 9. And to deal with the 9, I'm going to do 1 over 9. And then I'm going to add the 6. Rule 3, don't forget your 0. I'm sorry, don't forget your constant. Okay. Now the last one, and I cannot stress this enough. Always take the derivative and check. Always check them. And I cannot stress this enough. I'm going to be like, instead of being fun guy, I'm going to be like, always check your derivatives, your antiderivatives. Always take the derivative of your antiderivative. Always check it. Even if the problem doesn't say check it, check it. F prime of x equals negative cosine. I will wind up with negative sine, plus the 9 would hit that 6. It'd be 6 times 9 over 9. X to the 9 minus 1, 8. Plus 0, which equals sine of x plus 6x to the 8th. Always check them. 1 to 5, how do we feel about these 4 little principles? Okay, these are the 4 little principles that will save your life when you're dealing with antiderivatives. Okay, it's easier to take derivatives, so make yourself a table of the weird ones. When dealing with exponents, deal with the exponent first. Don't forget your constants, and always check them. Okay. I'm glad I have 5 people now watching my stream. That's very nice. Okay. Let's deal with one last thing. I'm almost out of time. I want ways to estimate my derivatives. I want ways to estimate what I'm doing. I'm sorry, ways to estimate AUCs. Okay. So let's start with this one. Let's let f of x equal the square root of I think 2 minus x squared might be a nice one. Let me see. So what I want to do, and this was the problem confronting Archimedes. And it's important to note that this was actually discovered first. So derivative calculus came along with Newton and Leibniz. But what's called integral calculus, which is the stuff we're doing now, the area under the curve, is actually older. Okay, this stuff is stuff that Archimedes figured out. Okay, now the connection between the two is the big deal for Leibniz and Newton. So I have this circle. In particular, I'm dealing with the area under the curve. I'm dealing right now with the half circle on top. Come here. Okay, well, it's not perfect. So what I'm dealing with is the half circle on top. And what I want to do is I want to estimate the area under the curve. In other words, I want to estimate this area right here. So what Archimedes figured out to do was this. He'd have this here, and he'd say, okay, well, what happens if I draw a square or a piece inside of it here? And I measure that area. Because squares or rectangles are very easy to measure the area of. And he said, okay, what happens if I do this area and this area here, and then do this area here and this area here? And then what I'm going to do is I'm going to add that area there, and that area there, and that area there, and that area there. So what he's doing is he's using smaller and smaller and smaller squares, or rectangles. Okay. Well, what Riemann did was say, okay, that's a good thing, but now we're dealing with equations. So Archimedes is the person who figured out this. It's called the method of exhaustion. And what Riemann did was say, okay, but instead of going for the inside, let's make just rectangles. Instead of doing all of these, computing all of these points, let's just do rectangles. Okay. So here's what Riemann did. Oh, I'm on the wrong screen. Nope, wrong one. This one. Okay. So what Riemann did was this, okay? He's got a rectangle here. And what he's going to do is he's going to say, okay, let's add more rectangles. Let's add another rectangle. As a matter of fact, let's add many more. But let's go here. I want an underestimate from this point here to this point here. Then this point here to this point here, 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 and so on and so forth. So he's always getting an underestimate of the circle. Okay? Well, then what he's going to do is he's going to say, okay, what happens if I use more rectangles? And notice what happens here to this number. This is the rectangle, the number, the measurement of these rectangles. So as I go on, I'm going to get, and remember the exact area of this figure is pi over 2, right? Because it's half a circle. So as I add more and more rectangles, I wind up approaching this number that's the actual area of my figure. How do we feel about that 1 to 5? Of course, there's nothing really special about using the underestimates. What happens if instead I always want to use an overestimate? What happens instead if I start with one rectangle on the outside of the circle? So this is something that holds the circle in it. And then I use smaller and smaller overestimates of the area, because rectangles are easy things to calculate. So now I'm always overestimating the area. But notice that this area right here and this number right here approximate each other. So what I'm doing is I've got this function called area under the curve, and it's moving from left to right. Okay? So my function is area under the curve, and it's moving from left to right. Right? The function's moving, and it's going. Now, what I'm going to do is I'm going to freeze it. I'm going to freeze it. It's going to freeze. There we go. I'm going to freeze it at a point. So my area under the curve is sweeping out, and now I'm saying stop. Let's estimate the area at that particular x. Okay? So to do that, now I'm at a particular x. Now I'm going to draw rectangles underneath this thing. Okay? Just like before, when we had the derivative, we froze x and then talked about the derivative at x, right? And we got the slope of the line tangent to the curve at that particular x by doing approximations with secant lines. I'm doing the exact same thing here, except now I'm doing approximations of the area. Okay? And there's nothing particular. So now I'm getting more and more approximations of the area. So let's do something that's not a circle. Let's do something that's more interesting. Let's do something that's area under the curve. Here's 1/2 x squared. Here's the area of this curve. Okay, so I've frozen x. I've stopped this curve going from, this curve started way over here at -2 and went to 2. And I said stop at 2. And now I'm going to use ever increasing numbers of rectangles to estimate the curve. How do we feel about that, 1 to 5? However, there's nothing particular special. I mean, there is something special about using over and under estimates, okay? One of them, I always wind up with an underestimate, and then the other, I always wind up with an overestimate. But I don't have to. I can use right rectangles or left rectangles. And this is where we'll pick it up next time with the formal definition of this thing. Okay? So I could use right rectangles. These are left endpoints. So here I'm going up and creating the rectangle there. Here I'm going up and creating the rectangle there. And then what I'm going to do is I'm going to get more and more and more left endpoints. And I could do the same thing with right endpoints. And my rectangles can have 0 height. They can have negative height, right? Here's one with negative height. Okay. So I can do all these different things. We're going to pick this up. So the intuition, we'll pick this up next time. And then you're going to do one you're going to do one example during your peer leading this week. And then what I'm going to do is I'm going to post a new website that's going to be due Sunday. There's going to be one for tomorrow, but then there's also going to be one for Sunday. And Sunday is going to have a couple more of these where you actually compute them. And then we'll get into the formal definition of the integral next time. Are there any questions? Okay, so today we went over AUC left of the base point, some tips for dealing with antiderivatives, and estimating AUC using rectangles, so introducing the Riemann sum. We're going to get to the formal definition of the Riemann sum next time, which the Riemann sum is easier to understand than it is to write. Writing it's a pain in the neck, but understanding it is easier. The intuition is faster than the definition. So we're going to pick it up there next time. If you have any other questions, I'm starting office hours. I'm sorry I went over. I'm starting office hours in 5 minutes. Let me just run downstairs and grab something to eat. All right. Okay. So I'll see everyone later.